Hello everyone. Now in this session we'll discuss about quantum computing, the next generation computational paradigm. But before going to start with quantum computing, we must have to understand the concept of classical computing. Classical computers. For the last several decades, almost every technological advancement has been powered by classical computers. Classical computers may be laptop, smartphone, server, smart computers. So for example, if I have two numbers, 2 plus 2, I want to add these two numbers. Computer cannot understand what is 2. Computer can only understand the binary numbers. If I am giving any name like Ram, computer cannot understand what Ram is. And suppose if I am giving any image, then computer system cannot understand image as well. Because we know very well that computer can understand only two languages, that is 0 and 1. So the classical computer process information using bits. A bit is the smallest unit of information and can exist in one of the two states, either in 0 or 1. So whatever the value you are giving to the classical computers like 2 plus 2, classical computers can convert into binary number, that is in the form of bits, and it will process with the help of logic gates, that is AND, OR, NOT, XOR, NOR, like that, and then display the output in the desired format. So this is the working of classical computers. Now, the tremendous success of classical computer has enabled the development of artificial intelligence, cloud computing, robotics, medical diagnosis system, autonomous vehicles, and many other applications. And this is done only because of reliable and deterministic result, powers modern AI ML cloud computing database and software systems, highly optimized hardware and software ecosystem, is scalable using GPU, CPU, and distributed computing. But there are few key limitations of classical computer system as well. The first is exponential growth of search space. If the problem is increases, the growth of search spaces also increases. For example, if I have 50 binary variables, it means there are 2 power 10 possibilities of search space we required. That is approximately 1 quadrillions plus. The second is complex optimization problem that occurs in machine learning. Problems such as feature selection, hyperparameter tuning, scheduling, route optimization, it becomes increasingly difficult as problem size is larger. The third is simulation of quantum systems. Simulation of quantum systems, it means simulating molecules, atoms, and quantum interactions. Enormous computation resources required. Classical computers struggle to do this. Fourth point is high dimensional feature space. In machine learning, often we require feature engineering, and for feature engineering, we are using kernel methods, high dimensionality representation. So as dimensionality representation, computational complexity also increases. And the last is energy and resource consumption. When we train an AI model, we need large GPU clusters, we need massive storage and significant power consumption. So these are the key limitations of classical computing, and to keep all the limitations in mind, quantum computer can arises. Scientists realize that some problems are fundamentally difficult for classical computers. Nature itself behaves according to the law of computer mechanics. Therefore, instead of fighting quantum effects, researchers propose using them as computational resources. This idea gave birth to quantum computer. Quantum computing is not intended to replace classical computing. Instead, it is designed to solve a specific class of problems much faster than classical computers. Qubits. Quantum computing is a new computational paradigm that uses the principle of quantum mechanics to process information. Unlike classical computers that use bits, quantum computers use qubits. Qubit means quantum bits. A quantum can exist as 0, 1, both 1 and 0 simultaneously. This unique property is known as superposition. Now quantum gates. Quantum gates change the state of qubits and enable quantum computations. They are the fundamental building blocks of quantum circuit and make it possible to perform operations such as superposition, entanglement, and interference. Now, the three basic fundamentals of quantum computing is superposition, entanglement, and interference. We will discuss one by one. The first is superposition. Superposition is like take all the possibilities together. It means it is the ability of a qubit to exist in multiple states simultaneously before measurement. For example, suppose you have a coin. So coin have two sides, either head or tail. But when you flip the coin, then in that case, in the fraction of second when the coin is in the air, it may be head or it may be tail. We cannot identify that particular state the coin is head or coin is tail, right? So it is like that. When the coin is on the table, it may be head or tail. This resembles a classical bet. But now imagine the coin spinning rapidly before it lands. It is neither purely head or not purely tail. It represents a combination of both possibilities. This spinning state is analogous to quantum superposition. Superposition enables parallel representation of information, exploration of many possibilities simultaneously, and quantum speed up in certain algorithms. The second is entanglement. Entanglement is one of the most remarkable property of quantum mechanics. Two or more qubits become connected in such a way that their states cannot be described independently. The state of one qubit is directly related to the state of another. Entanglement provides a strong correlation, quantum communication, quantum teleportation, and enhanced computational power. Third is interference. Superposition creates many possible computational paths. However, not all paths lead to the correct answer. Quantum computers use interference to amplify correct solutions and suppress incorrect ones. Interference helps increase probability of correct solutions, reduce probability of wrong solutions, and extract useful information from superposition. It will extract useful information from superposition. Now the question is, what is the difference between quantum computer and supercomputer? So basically, if we talk about supercomputer is nothing, it's a classical computer. It is much faster than a regular computer, uses individual of CPUs and GPUs working together. Quantum computer is fundamentally different because it computes using qubits and the principles of quantum mechanics along with powerful hardware. Now, the application areas of quantum future. So the first is drug discovery. Developing a new medicine is a long and expensive process. Scientists need to study how different molecules interact with each other, which is very difficult for classical computers. Quantum computing can simulate these molecular interaction more efficiently, helping researchers discover new drugs faster and at lower cost. Second one is cryptography, quantum cryptography. Cryptography is used to protect sensitive information such as online banking, emails, and digital payments. Quantum computer has the potential to solve certain mathematical problems much faster than classical computers. This is why researchers are also develop new encryption method called post-quantum cryptography to keep future communication secure. Next application is AI/ML acceleration. Artificial intelligence requires large amount of data and powerful computers to train machine learning models. Quantum computer can help speed up complex calculation and optimize tasks. Although quantum machine learning is still in the research stage, it has the potential to improve applications such as medical diagnosis, fraud detection, and recommendation systems. The last application for quantum future is logistic and robotics. Logistic companies need to find the best delivery route, manage warehouse, and schedule transportation efficiently. As the number of routes increases, these decisions become more complex in classical computers. But for quantum computing, it can help find better solutions more quickly, reduce delivery time, fuel consumption, and overall transportation cost. So that's all for quantum computing. I hope this session has inspired you to explore the fascinating world of quantum computing. Thank you very much.